Ladies and gentlemen, welcome to our session today on powering the next industrial era. We lack not for ambition here at Davos. We are here to look into the future and see how we build that future. Am I right, gentlemen? I'm delighted to be here. I'm Vijay Vaitiswaran. I'm the Global Energy and Climate Innovation Editor of The Economist. And of great interest to me is the topic as an engineer by training myself from MIT. I've been following this technology for a number of years, as well as developments in AI, which I write about closely for us, and the linkage with energy. And this really brings these topics together in a very, very interesting way. To my immediate left, we have Eric Schmidt, known to all of you, a former CEO and chairman of Google and chair and CEO of Relativity Space, and Bob Mumgaard, to my far left, co-founder and CEO of Commonwealth Fusion Systems. Please give them a round of applause to get them going.
Thank you.
They are going to give us a look into the future, but not really so distant future. Am I right, gentlemen? They've written a very interesting and provocative op-ed that's up on the World Economic Forum website. I encourage you all to take a look at it. Just to get a pulse of the room, how many of you in this room would say you're quite familiar with what fusion technology is? Hands up. Okay, this is great. At least a third, which is great to know. That means there's two-thirds that are yet to be wowed by what's coming, but also maybe skeptical, or may have heard it's one of these classic, always the energy of tomorrow, and we'll stay that way. So we'd like to update that view, but also to point out what needs to happen to make it a reality. So Bob, maybe we can start with you. Commonwealth is the leading fusion company. I think you've just finished a round of funding that gets you to close to $3 billion in funding, if I'm not mistaken. And you're pioneering some technologies in Massachusetts, but ultimately, I think, to build your first commercial power plant in Virginia. Can you give us a quick update on where's fusion got to, and why should we take this, again, this utopian technology of the future seriously now?
Yeah, well, I think first for the two-thirds that don't know what fusion is, I'm going to give you the 30-second answer what fusion is. So and you can take it from me. I'm an MIT fusion guy. So what is it? Fusion is a physical process. It's actually the most common process in the universe. It's the process that powers all the stars. And that process takes light elements, combines them together, and makes energy. Now, why is that interesting here on Earth? It's because if you were to do that, if you were to build machines that create this process inside them, you would have machines that, once they were built, would make energy, as much energy as you want, for as long as you want, wherever you want, whenever you want, without consuming anything. So they wouldn't need to be part of natural resources of digging anything up or transporting it or waiting for the wind to blow or sun to shine. It would just be machines that made energy. And that's a big, big shift in how to think about energy. Because up till now, we're sort of still in the hunter-gatherer mode of energy. And when you go from that to, hey, you make better and better machines, faster and faster, cheaper and cheaper, that have this reaction inside them that will never run out. We will literally never run out of fuel. And the fuel is available for everyone. And there's no externalities, long-lived waste or runaway reactions. That is deeply sovereign energy. That is energy that could be used to do energy intensity at levels that are 10 times more than what we do today. So what would the world be like if you had 10 times more energy? And that is a big, big idea.
By the way, you forgot climate change.
There's also, it doesn't make any emissions, which is useful.
Yes.
So there's no one on the ins and outs. It's like it has no ins, so there's no one to fight over pipelines and supply chains. And there's no outs, there's no one to fight over what comes out of it.
So Bob, as Eric rightly pointed out, the local emissions, let's remember, millions of people a year die from the local emissions of the way that the world uses energy today, fossil energy primarily, but also on greenhouse gas emissions. You have a benefit on that. But on the supply chain energy security, you've talked about advantages. And in terms of the opposite of intermittency, having reliability, firm power, that is a huge demand, particularly from AI and data centers, but industry as well. You see multiple benefits, and this can be also distributed in fashion. Over time, as you say, and has the potential as yet unproven, of being scaled, applying economies of scale so that you get cheaper over time. So this is the vision you're laying out.
That's the vision.
Right? And so just so people understand why the enthusiasm, that's always been something of a vision, although we've moved away from maybe the biggest of big science ways of doing this to now you're a commercial enterprise. You're backed by private companies, including if Google was involved from the beginning, but also doubled down on the next run. I think also is one of the off-takers for what you hope will be a commercial facility in the 2030s. Am I right?
That goes to the timeline. So, the vision's been there since we basically understood how the stars worked. But what we've seen over the decades of research is we've been able to actually make this reaction happen here on Earth. We've developed classes of machines. There's different sort of architectures. And we've now recently, just in 2022, in the United States, built a machine by the national labs that made the fusion reaction happen at a level that made more energy than it took to create the conditions to make this very hot thing.
Is the ignition facility
The National
at
Ignition
Livermore.
Facility at Livermore, exactly. And that's really a triumph of going systematically into science of how this reaction happens and what the right conditions are. And that scientific journey has been very, very fruitful. But now what we see is we're starting to see that move away from just the science and become commercial. And this has happened in the past of all the other big industries we have today. At one point, they were a science, like making aluminum was a science, and now it's an industry. And fusion's going through that transition right now. And so you have the sciences has been proven.
Yeah.
No question, can this be done? Now the questions are, what's the most effective way to do it? How to scale it? How to get it out into the commercial market? You've got companies emerging, so we're one of them.
Let me stop you there. So you've laid out the case, I think, and hit some of the key points. But there may be some in the audience suspecting you're talking your own book. You are the leading fusion company. You've raised tons of money. But you got to the point about private sector. There are dozens of companies, in fact, startups of various size, Europe as well as in the US, and there's government efforts in China as well. We'll talk about that, I'm sure, in due course. But the point is there's a global race. This is not one company, one technology, but rather the science is advancing. We're to the stage of engineering, in fact, advancing, and as well in terms of the financial models. And that's where I want to come to you, Eric. You've scaled multiple world-changing technologies in your career. Give us a bit of a handicapping of this race. How do you see how excited are you? What's interested you in this topic now? What's the potential? And in practical terms, how does this move forward?
So first place, if you look at models of climate change, they're completely determined by what assumptions you make about clean power that's baseload. So if you assume that fusion and fission are your only clean powers that are baseload, which we can debate.
Some geothermal guys would complain, but leave that to the side.
We can add geothermal in if you wish.
Yeah.
And again, we'll see if that scales at the level of fusion and fission. We're going to have to solve the energy problem for the globe because as much as I'd like it, the fact of the matter is people are not going to use less energy. People are going to use more energy for all sorts of things, including AI. So we have to solve this problem. You're well aware of the state of fission in the Western world. Here in Europe, most of the plants have been shut down, except for in France. In America, there have been a few starts. Most of them have gone bankrupt and so forth. This week, by the way, the group that regulates this appears to have changed the standard by which you measure the emissions and the certifications of nuclear power. This is fission power, and that's a welcome thing because it was really throttling the industry. But fundamentally, we all need more power. Bob is a hero of mine because he took his PhD in fusion stuff, and in particular in tokamaks, and he figured out that he needed a new set of essentially magnets. Right? And so the first thing he did to get to where he is now, he solved a different problem, which is a magnet. I'm involved with another company, which is an alternative technology called essentially a form of pinching, where you pinch it with a pulse. And that requires a capacitor. And again, that company invented a new kind of capacitor. So the interesting thing is that we're finally now not doing science, we're doing hard engineering, right? So your company is going to be successful because you spent years and all of that money to figure out a much more effective way of handling essentially the race that goes around in the tokamaks. You'll say it more accurately than I. So where are we? We're in the beginning of the engineering phase. Now, how much time do we have? You can look at climate models and decide. The core problem we have is that if you make reasonable assumptions, I'm going to use Q greater than 1, which is a statement of excess power for you in 2030, 2031, some number like that. I noticed you didn't make
27, 28.
You didn't make a claim. I had to go to make a claim.
27. Yeah.
27. Is that next year?
Yeah.
Excellent.
You heard it here, folks.
You heard it here.
Well, it's been consistent for like 4 years, but yeah.
Okay. Well, next year. So net facility gain of Q greater 1 would be incredible. The problem, of course, is you have exactly 1. And there is this huge scaling problem. And the scaling problem can be understood as follows. As much as I want the private market to do it, we're going to have government's help. There are no global energy sources that did not have significant government funding and help and credit and backstopping and so forth to build it because the capital requirements are so high. It's very different from software. So the way to understand the problem is, first, his stuff has to work. These other challengers have to work. We have to have the competition. There will be multiple winners. That's clear. And that's good. That competition is great. Then you have to scale. Now, you start doing the math, which is why I got interested in this. How many electricians does it take to build a nuclear power plant of fission, fusion, whatever? More than we have. More than we have in America. The demand for electricity, if you just look at data center loads, demand over the next 3 to 5 years is about 80 gigawatts. As a reference point, a nuclear power plant today is about 1.5 gigawatts. Your demonstration site is?
400.
400.
Megawatts.
And that number has also been the same for a long time. I think you told me that the 400 was interesting because it fits right into the old coal-fired power plants. You can literally just take the steam engine out and put a new steam engine in. So it's
Use the
Virginia
connections, use the infrastructure, the same.
So you don't have to
apparatus.
rebuild. This is a clever, again, a good engineering, good business decision. But if you start thinking about the amount of power that we need, you're not going to get there by these kinds of techniques. You're going to have sovereign wealth firms investing large scale. So a team that I work with has built a plan for what it's going to take. Again, you're the physicist, I'm not. What are the hardest materials in a fusion plant?
Yeah, that's one of the interesting things. Like, to build a new energy industry of any real significance, you're talking about building like 10,000 plants. Like, that's a good round number. If you do 10,000 plants, you're the largest energy industry. That's the number of 737s in the world. So that's the number of Walmarts. So that's the scale. But most of the stuff is like steel, but it's steel that's all in the right spots. Right? There's a lot of intellectual property, a lot of know-how that goes into making the steel and the right stuff. There's some rare earths, but they're like dopants. They're small amounts, again, in the right spots. And so there's not a bottleneck on something you dig out of the ground. But there's a bottleneck on how do you get the stuff into the right shape. So manufacturing. So if you look at our supply chain, 1,300 firms, 30 countries, and like they are everything from people building that would be normally building reactors for oil and gas, for, say, crackers, so big weldments and steel structures, to people making chips for fast-charging EVs. And so it dovetails with this existing supply chain, but you have to convert it. You have to build something that's like the size of the aerospace supply chain.
Bob, does that call for something like a kairetsu model, like the Japanese auto companies, or even the tier 1 suppliers in the US? Is that what you're developing?
Yeah, it's basically what we're developing. I mean, today, it's a lot more nimble than that. You got to think of it, you're developing something that is like the early automobile supply chain, where you're like going from ones and twos to like, okay, now we're going to make a bunch of them. But you have to have the same people, you have to have the same expertise, and you increasingly automate it as you go. There's pieces of our supply chain that look like that, and there's pieces that look like someone who's got an existing supply chain, but they're sort of diverting one every once in a while and doing some retrofit to it.
Yeah.
And eventually it will look like a supply chain for building rockets, planes, and hopefully like an updated supply chain, because you get to start over in some cases. So when you think about the role of generative design, the role of additive, like that's all very beneficial to fusion.
Eric, I want to pick up on...
So if I,
yeah, go ahead.
if I can, I think based on that, I think the rhetorical question goes something like this. Do you fundamentally think that the state of fusion will end up with the equivalent of TSMC in Taiwan? Now let's think about what actually happened. All of this technology was invented in America a long time ago. A bunch of clever people moved it to Japan and Singapore. And then a particular founder who went to Berkeley became dissatisfied, went to Taiwan, convinced the government. They put an enormous amount of money. And I think people do not appreciate that the Taiwanese success in semiconductors was direct industrial policy at a scale that in America, at least, people would blanch. It may take that. If it takes that, then there will be nationwide winners who do it. It may not. It may be a little bit easier. Aerospace is not quite as concentrated, but also look at aerospace, concentrated in geographies. Southern California for a long time. Seattle was a long time, so forth. You go to look at jet engines. Why are there only 2 providers of jet engines, and why has it been so difficult for China to build the third jet engine because the stuff is hard. And if you think jet engines are hard, trust me, fusion is harder. I know because I manage a rocket company.
So it is literally rocket science, or even harder, as you're saying. Just to put you up a challenging question to you, Eric, because you've thought a lot about the commercialization model. You've teased us that you've got a plan, a master plan, involving, I think, sovereign wealth funds or some other manner of funding. Maybe we can talk a little bit about that. Certainly the people at Davos, in this room and outside, could well be interested in hearing that and being a part of it. But the challenge is this. The U.S. got very animated about energy security, energy technology, resilience, a couple of decades ago in the wake of the oil shocks, and we invested in the Synfuels Corporation. Europe, in the wake of the Russian gas cutoff, got behind Northvolt, for example, as something of a local champion, European champion on batteries. We know the story there. It didn't work out. How do you guard against money poorly spent when it is directed in a particular technology? What's your sort of lessons from history to prevent that happening?
Well, what happens with these things is everybody talks about the failures, of which there are plenty.
Sure.
But you don't talk about the incredible successes.
Well, you've mentioned airplanes already, of course.
But let's
right?
think about the GPS,
Yeah.
right? The GPS essentially changed everything. Again, Air Force satellites in 1970s. I would say that in America, fracking, right, is another example of such a success. There are plenty of successes as well as failures. The question is, how do you get an industrial policy that does not constrict it? And in general, my view has always been that the right thing to do is to have low-cost credit, low-cost loans, and so forth, and let the commercial sector do it. Another way to say this is if you had the right, essentially, access to capital, you could build businesses in energy that are massive.
Yeah.
Now, let's think about how important is it to get to fusion? It's immense. If you have enough capital, should you be in that business? Absolutely. Now, in practice, it's more capital than any one of us can raise. So that means we have to piece part it out. And I'm quite convinced, in my understanding of how this is going to evolve, that there will be a series of supply chains. There's the ones that you described. At the end of the day, these reactors will have specialized parts, and those specialized parts will be built probably by one supplier. And the country that figures out where all those suppliers are and gets them in their own country is probably going to have a leg up. If I were to guess, I would guess Taiwan and Korea have the sort of attitude and structure to do this, perhaps Japan. But if you think about the way Korea works and Taiwan works, they are able to do these things at scale. Think about the Korean shipbuilding industry, for example. They're amazing at it.
Yeah, world class. Since we're talking about countries, I know you've done some deep analysis on how China's fusion efforts are going. So it's really a question for both of you. There's no secret made by the Chinese. They're investing heavily in fusion. I think their leading effort looks curiously similar to what you're up to, Bob, without casting any aspersions on how they got there.
What a shock.
Yes, exactly. But nevertheless, China has a success in lots of areas, but they're also not good in some areas. The example of aerospace. I used to be our Shanghai bureau chief, so I followed the development of their engines very carefully, and they have not caught up with the
By
West.
the way, why was it so hard? Come on, it's just jet engines. Give me a break.
Right.
12,000 RPM. What's
Exactly.
wrong with you? Why
Exactly.
couldn't they do it?
One top executive at one of the leading jet engine companies in the world explained to me, there are things that happen that are at the edge of supercriticality that don't follow the rules in the textbooks. We don't share that information. We don't publish. In other words, and I see you're nodding your head. You know, in plasma, you're finding this out day by day, that there are things that happen that don't follow past, and that makes it harder to cut and paste and cheat and copy. You have to invent and learn by doing would be part of my answer.
Yeah, I'd say an example of fusion fits in this category like jet engines, rocket engines, where you're harnessing complexity. Like you are creating systems that use the same laws of physics, but they are able to do like really nonlinear things, very complex things. And that is very different than like just a commodity. That's very different than building 1 million battery cells, for instance. Right. Building one jet engine is much harder than building 1 billion battery cells. And the gains compound in those systems. So like the better you make the fusion plasma work, then the less you need to make the magnets work, and the better and lower cost the magnets become, and the whole thing compounds. And so we've seen that the Chinese have invested. They're starting from a less mature overall innovation ecosystem, less mature fusion-specific ecosystem. They've used open science to learn a lot, and we've actually, there was the government's policy in the United States to teach them everything that we knew, circa 2000. And so that, maybe in hindsight, was short-sighted. But they've sort of caught up to where the state of the art was in the 2010 timeframe. But they've been able to do it fairly quickly, but they've been able to do it by mobilizing large-scale effort. So these are technologies, because they're complex, you need supply chains, you need construction, you need large capital, and there are some advantages to a state-planned system in that way. The Chinese have a state-owned entity that is basically a roll-up of the Chinese National Nuclear Corporation, China Grid, the banks, all rolled up and said, let's go make fusion happen in China, right now focused domestically, as quickly as possible.
Can you, both of you, I want to turn to AI in the time we have remaining. Talk about, Bob, we'll start with you, how you're applying AI in pushing the frontiers of fusion. And if you want to jump in.
Can I just answer your previous comment? You understand the Chinese model is basically dual circulation. So the Chinese government policy is self-reliance for many, many historical reasons. So everything Bob said is consistent with that. That is not the policy of the West, right? It's a different policy. So that sets up the race. I'm sorry, go ahead. I know.
Yeah, no, fair enough, indeed. And I want to come to you on AI in a moment. But last year at Davos, at a dinner, we were talking, and I was asking you, how is AI influencing what you're doing? And you explained that at that time, a year ago, that you were already utilizing it not only to do things more efficiently, the idea of making processes more efficient or data gathering, but even to do things, you could use it to enable you to do things you couldn't have done before. It was a tantalizing thought you put out there in the last year and going forward. Can you talk a little bit about how AI might actually be affecting how you do your frontier engineering?
Yeah, so actually we just announced a long time, it had been under wraps for a long time, a partnership with DeepMind, where they've embedded with our team and MIT and others. And what they're working on is you have these giant computer simulations of plasmas. I mean, these are some of the largest simulations that civilians have ever run. You're talking about using a DOE supercomputer for months to get a single data point. Well, you can use AI to interpolate that data point, to start to ask the question well, the next time I run that giant computer, what's the most useful data point that would make the AI training even better, right? It's guiding itself and feeding back into the academic ecosystem. Then on the other side of it, you have this machine that's making a star inside of it. It's literally a star in a bottle. And the more that you can tune that bottle and play with that star, the more performance you can get. You can get factors of 2, 4 of performance out. And today we use rules-based control algorithms. So thinking a human wrote a code. Well, now we have AI that's trained off of the simulations to know what to do to fly that star. And those are just 2 applications. There's about a dozen or so applications that people in Fusion are working on, and many of them are now at the stage where they're incorporated into our factory or incorporated into control systems. So it's super exciting to be able to basically harness complexity using intelligence that can think way faster than us, so you can put it in loops to control things, and also that can see and understand much bigger sets of data in a way that even our best physicists couldn't parse.
Great. So you see a great opportunity for applying AI.
Absolutely.
And you're doing it. Eric, if I could ask you the other side of the question. Energy is, especially in the headlines these days, especially in the West, seen as a great bottleneck for development of AI. It's no big secret. If those of you may notice some red mud on my boots, the last time I pulled out these boots was because I needed to buy extra high ankle boots to get a tour of Stargate out in Abilene, Texas. These are the red sands of Texas, as I was given a tour by OpenAI of their facility, Oracle, and those guys over there. They said you have to have them extra high because of the rattlesnakes, or else you're not allowed on the tour. I'm not claiming there are any rattlesnakes, but there are other perils, I'm sure, at Davos we all need to watch out for. The white snow on my boots at this point. Can you tell us the energy constraint? How serious do you see it for development, and where does fusion come in that picture? Because it will be a while. He's already given us some timelines, but realistically, it's going to be a while.
So the problem is that we don't have enough time. Assuming CFS is the first one and the others are coming very soon, the productization takes into the 2030s. You're building a demonstration plant, 400 megawatts, then you're going to build a real plant, right? These things take years. We don't have that time. So the current situation, my simple model is you have a race between China and her friends and the US and our friends. And the race is for intelligence. And intelligence is the most important race there is. Not a war, it's a race, right? Chinese have a different approach than us, and we have a different approach than them. And us includes the Europeans and obviously DeepMind and the UK.
Let's hope it does. We'll find out in the next day.
I hope so.
Yeah.
I think we're all transatlanticists here in the church. So one way to think about it is China has plenty of excess power. If you look at the amount of solar power that they've deployed in their country, largely to address their own climate change, it's something like 120 gigawatts of new solar and various other renewables has been deployed in the last few years. The numbers are staggering when you look at the charts. So China does not have an energy problem. They may be building fusion, but they don't fundamentally have an energy problem for AI. Whereas the US has the opposite. China does not have enough of the right chips. We have the very best chips, which we're very proud of, which we typically don't let China use, and they're doing their own.
Right.
And then we don't have enough power. What's the gap? So I set up a data center business recently, and so I've been talking to all the companies. And if you sum their needs for the next 3 to 5 years, it's around 80 gigawatts. Now, nuclear power plant, 1.5 gigawatts. As I said, so how many of your things is that, right? That's like a lot. You're going to be a very happy guy when we buy all that stuff. So just get it to work, and it'll be bought. So that's the set problem. Right now, the solution is largely natural gas, and they use these combined cycle turbines, which are in short supply.
Yeah.
And so there's a race.
The 4-year wait list from GE
Yeah,
Vernova.
so there's a race inside of America of who has access to pre-orders of GE Vernovas,
Right.
and I have 6 and I have 4 and so forth. And the grid is interesting because the grid is, the way the grid works is there's a grid auction, and you can only add to the grid if you can guarantee stable power. And because if you're a new person coming in, you can't guarantee stable power. They're very worried that you're going to come in and screw up the frequency, if you will, of the
With
signal.
good reason.
For good reason.
Yeah.
So it looks like the grid capacity is at practical limits done, not because of lack of power, but because of the requirements for comity and ability to work together and so forth and so on. And so people are now building what is called behind the meter.
Or bring your own power.
Yeah, the term in the industry is behind the meter, but it's bring your own power. And when you say bring your own power, you mean one of the turbines is as big as this church. And it takes 2 years to develop and so forth.
Right.
So what's interesting, just for everybody's benefit out of interest, what is the current #1 problem in the AI companies? Lack of data centers. What do they need data centers this year, which you're not going to do and I'm not going to do and so forth?
Right.
That's how severe. And you sit there and you talk to them, which I know all these people, and I say, is it real? And they go, yeah, it's directly related to the revenue of the company. So the demand is real.
Right.
There are many people who think this is a bubble. I don't.
Yeah.
But I'm sure that at some point the demand will S-curve, but we're not there now.
So build it and they will come.
They will, at least for some number of gigawatts, maybe 80.
Right.
And to the economic point,
Yeah.
you can trace it all the way back, right? Like you can look at the valuations of these companies, you can look at what their capex is, you can trace that back to what they assume the future revenues from the compute is, and then you can ask the question, how much compute is that? You can ask the question, how much power is it gonna need? And like you get curves that look very, 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 very scary. Because in some ways, of that whole industry, the least innovative and the slowest moving is the power part of it. The bottleneck is the power. It's not actually
But
the
you know,
rest
Bob,
of it.
the reason, at least one of the reasons in the West, let's bear in mind, this is a global conversation. Air conditioning is going to be a much greater contributor to energy growth than electricity load in the developing world than AI will be for some time yet. But if you talk about the Western markets, in the US, there's been flat electricity demand growth in the last 20 years, roughly. Europe, comparable. And so these are industries that were rewarded for keeping the lights on, for keeping things safe and stable, not rewarded for risk-taking, new technologies, for innovation. On the contrary.
Even just think about the people in those industries. Many of the people that are staffing the entire chain, so from the utilities to the suppliers of the utilities, have been in companies where they have never seen growth.
Right.
And we're going to ask them to grow at rates that look like tech companies.
So, which will be exciting for them. So one of the things to remember is that there are 2 industries that you should invest in as a national priority because you can make money at it. The first is telecoms, and the second one is energy, right? Furthermore, the energy infrastructure in a country is turned over every 30 to 40 years, right? So there's this constant build-buy cycle. So a simple model is your stuff shows up and it just naturally goes in, you make lots of money. However, the demands, as you pointed out, especially in the global south, especially with things getting hotter and so forth, it's going to be incredible.
And energy fundamentally equals prosperity. Like, you can look at the history of Human Development Index, and you can plot it against energy, and one-to-one, most predictive correlation in that whole data set.
Also, the people here in this audience travel, go to countries which have unreliable power and talk to the people running the countries about what it's like to get people to build factories, right? You can't run a factory with unreliable power.
We have, I'm glad you mentioned governments. We have just a few minutes left. I want to use that time to ask both of you, if we have this very attractive roadmap you've laid out for us, how in the next decade we could see not only the realization, but maybe the scaling up of fusion, the backbone of maybe an AI economy and other parts of the industrial economy as well, and of society. What do governments need to do now? What would you like to see, each of you? I'm going to ask you to be specific on what governments need to do, either in policy or a market design, for example. There's a lot of things we talked about, electricities and utilities and incentives. Go anywhere you want with it, maybe finance. What would you like to see, one or two concrete things to give people something to take away from this conversation?
So there's, in the fusion side of it, there is a push right now. Like, if we wait on the fusion side and wait for it to evolve somewhere else, like, we will lose the ability to steer how it goes. So governments that lean in and invest in the first generation of plants, that invest in the ecosystem around the fusion developers, that's the supply chain, et cetera. Those are the ones that are going to control the agenda. Those are the ones that everyone's going to go to see how this is done. Those are the ones that are going to propagate the standards, the regulatory, and the entire environment that goes with making power. That's a very, very powerful thing to do, but it needs to be done like now. And like the bill for that is in the billions of dollars. It's not in the tens of billions of dollars. But the cost to recoup it later, if you miss it, could be very, very large. And so, we have the Fusion Industry Association has at the U.S. right now a proposal. It's a $10 billion. This is exactly how you would spend it. That would get you to the first generation of fusion power plants on the grid. Construction starts on those plants within this current administration.
Bob, let me press you on this. You mentioned your industry association. My experience following the politics of energy in Washington and Brussels and so on, the biggest meaningful competitors for solar was not the fossil lobby or the enemies. It was the wind lobby or the battery guys once told me when I asked them why you're such a great solution, grid storage, energy stability. Why aren't there more? They said we don't have as good lobbyists as the solar guys, and so on. Right? In other words, it's a pointed way of asking you: is conventional nuclear fission your greatest enemy on Washington?
No. We're in a moment right now where we need a lot of energy. So everyone's scrambling for what their best story is to just compete against time. So the competition right now, when you're talking early stage development, innovation, getting things going, the competition is not market share, it's time. And so that's a good place to be, because it also means that there's things that you can do together. We work well with traditional fission in many of those policy areas.
Eric, how about you?
If you think about the 10 billion of research, that's the same number that was in the CHIPS Act for research in the US for semiconductors. So we should be able to build a political consensus around that. Energy is that important. We completely agree. You asked the question, what should we do collectively? We need more money for research. This stuff is very hard. It's just more research, more research, more research. People forget that in the 50s and 60s, there was an enormous amount of funding in aviation. Use that as a measure. Think about all of the research that went into this rocket programs and so forth. It was billions and billions of dollar equivalents. Now, we need that. Second, we need to architect what the supply chains are going to look like. It's early, which is why we're starting to talk about it, but I think it's relatively straightforward, right? You need to have approved and certified partners. You need to have an industry association that can make it happen. And you need investors. The investors will invest in private companies. One of the key questions for you as an investor is which companies, right?
Right.
And how do they get started? My guess is that that in each of the countries we've named, there will be obvious candidates to add this as a business, and that a partnership between, for example, a Korean steel manufacturer and the Korean government to build these specialized parts makes sense. It's something like that. And we can debate the specifics, but we're at the beginning of something which is massive. We don't fully know.
Do we need, you've invoked the airline or airplane analogy a couple of times, the equivalent of an Airbus or a Boeing, again, ostensibly, at least in the case of Boeing, very commercial entity, but clearly supported.
It depends on the answer to the question I asked you about Taiwan. If you believe this stuff is this hard, right, will it ultimately end up in one country with one enormous company, which is almost a quasi-government company? Right. We don't know. Airbus is such an example. They took two different groups and merged them because the economics and capital cost of developing things was so high. I don't know yet. I worry that what's going to happen is that fusion is so hard that you'll end up with two competitors as opposed to 5 or 6 or 7.
Even within a big national market like the
Even
US.
within because I think more competition is good.
Yeah.
And the reason, by the way, is not because the people are evil or hard. It's just capital, right? And just as an aside, in my industry, which is sort of data centers and AI, how many companies can afford $50 billion of capital to train the models and build the data centers? Companies, right? So here's your list. OpenAI, Google, XAI, whatever. Pick the Chinese. How many are going to make that? It's an enormous amount of capital in the world.
So is that the answer? The Bank of Big Tech is going to fund and develop fusion?
I certainly hope that the sovereign wealth funds are going to take a whole chunk of their money. If you look at sovereign wealth funds, just to stick on this, they are famously patient, long-term capital. These are markets that they understand, right? I think that that's the key message. Those of you in sovereign wealth funds, come talk to us, and we'll get you set up. It'll be the best career decision you can make.
Well, there you go. All right. Well, on that note, we're just out of time, I see. I'm going to say thank you to our two panelists for provoking. They put up with some of my somewhat rude questions, which I appreciate. And thank you all for your attention. You've heard it here first. We're going to go and visit Bob's facility when he's ready. Thank you.